All right, so in these notes, we're going to start talking about atomic structure, as in the internal structure of atoms. And you see an image here that depicts one of many different styles of representing atomic structure. This animation is sort of a combination of many different models of the atom. And we'll learn soon that models of atomic structure have evolved throughout history and have been modified as new evidence has emerged to sort of update or correct the model. And this is sort of a blend of several different models of the atom. It's a nice way of representing atoms, but we're going to learn about first the modern model of the atom. And this is going to be a little hard to draw in our notes. I'll show you a good way to do it in just a minute. But you can see that essentially we have a blur, which is the region we're going to call the electron cloud, and then hiding in the core of that is the nucleus of the atom. So we're going to first write some things down that summarizes these points. In other words, we want to make a note of the fact that the modern model of the atom is called the electron cloud model. And then we're going to try to draw that. Now, the way I'm going to try to draw that is by first drawing a dense core called the nucleus, and then I'm just going to lightly shade around it to represent this sort of blur of a region which we're going to call the electron cloud. And then we're going to make a sort of compare and contrast chart here that distinguishes between the nucleus, which I'm pointing to the very center here to describe that, and the electron cloud, which I'm pointing to just that whole region that surrounds it to describe that. And we're going to write a few things underneath each of these headings. So this blurred region, you don't really have to show it as a sphere, but we could think of it as roughly spherical in shape. And that is the electron cloud. It is a region where you are likely to find an electron. And that might seem like a really vague way of describing the electron cloud, but really the electron cloud is defined in terms of probabilities of finding an electron. You can't really tell exactly where the electrons are. And that's what's made atomic structure such a mystery over the decades and even centuries, is the behavior of electrons is really not like the behavior of everyday macroscopic objects. So we'll first note that it's a region where you are likely to find an electron. And then later in this unit, we're going to develop the idea that the electron cloud is made up of many shells. And I'm going to put the word shell in quotation marks, but this is a common way of describing the energy levels, is to use the word shells, but we will learn and we'll continue to talk about the fact that the electron cloud has many different energy levels or many different shells that electrons can be described as residing in. So we're going to have to develop a more sophisticated model of what electrons are doing soon, but for now I'd like to just suggest one off to the side on some scrap paper for a moment. If you consider the blades of a fan, let's say we are looking at a fan that has just 3 blades, then when the fan is standing still, we know there's only 3 blades there. But when the fan starts spinning, of course, those blades are going to be whirling around so fast that you can't really tell where any one blade is at any one particular point in time. We end up getting kind of just a blur of fan blades. And while we don't know where any one is at a particular time, if you threw a ping pong ball in there, it would certainly bounce back. If you put your finger in there, it would certainly bounce back or get hit by a fan blade. There is a region where you know it is safe to put your finger, and that would be like out here, you're not going to get hit by a fan blade, but anywhere in here, you will. So that's a good way of thinking about the electron cloud is just a region where you're likely to find an electron. But just like the fan blades are going quickly, electrons also, it's kind of hard to determine where they are in the electron cloud. On the other hand, the nucleus is going to be a little simpler to talk about. The first thing I want to point out is that the nucleus is very, very small and very dense. And it's the core of the atom. And it's really not to scale here. So even if I just made the tiniest dot that I can make with my pen, it still would be much too large. There are some great analogies that we can make about the relative size of the nucleus to the relative size of the atom, but we'll just for now say, very small, very dense core. In other words, all of the mass of the atom is really concentrated in that very small volume. And I also want to note that this is the location of the protons and neutrons in an atom. So the protons and neutrons are located in the nucleus. That's the modern model of the atom, the electron cloud model, and we have two regions here, two regions of the atom, the electron cloud and the nucleus. So we're now going to talk about those three elementary particles, protons, neutrons, and electrons. And we're going to make a data table here to describe some of the important information about each of those. We've got a lot of columns to make here, so we're going to write small. There's the type of particle that we're going to be naming. So for instance, protons, neutron, and electron. There's the symbol of the particle, and there's the charge of the particle. Now, we want to make those three columns about half the page, so we have room for two more things. One of them is the relative mass, so just so that we can compare them to one another. And the next is the actual mass of these particles, which is a little bit less important, but it will be kind of interesting to think about. So we may want to draw a line separating these columns, but if you just want to estimate, then that works as well. I'll go ahead and take the time to draw some lines here to make it a little bit more neat. There are going to be three particles we're talking about, so that's about how long that line should be. The particles that we're going to be talking about are protons, neutrons, and electrons. So there's a data table we can work with. The first thing we'll do is go across the row for protons here. The symbol for a proton is a p with a plus next to it, and that's because protons are positive. The charge is +1. So a pretty intuitive symbol for a proton. It's got a positive charge, and the magnitude of that charge is 1. And we're going to use a relative mass of 1 here, and all the other particles are going to be compared to that. So what's the actual mass of a proton? Well, it's a pretty small number, 1.67 times 10 to the negative 24th grams. That's a ridiculously small mass. The actual mass of the proton is not something that's especially important. I'm going to use that shorthand abbreviation for scientific notation here, but that's 1.67 times 10 to the negative 24th grams. Not a very large mass. But it'll be more helpful for us to think about the relative mass of these particles. In other words, if the mass of a proton is 1, the mass of a neutron is also 1. 1.67 times 10 to the negative 24th grams. Now, a neutron has a symbol for it as a N, and the charge on a neutron is not negative, it's neutral. It has no charge. So we have protons, which are positive, neutrons, which are neutral, each having about the same mass, and then finally we have electrons. And the symbol for an electron is a lowercase e with a dash for minus, and that's because an electron has a charge which is equal and opposite to the charge of a proton. So if we had 3 protons and 3 electrons in an atom, that means those cancel out and we have a neutral atom. The electrons, however, have a negligible mass, about 2,000 times less than the mass of a proton or a neutron. The actual mass of an electron is somewhere on the order of 9 to the negative 27th gram, so a really negligible mass, about 2,000 times less massive than a proton or a neutron. So when we say that most of an atom's mass is concentrated in its nucleus, then that should make sense because the nucleus is where we're going to find protons and neutrons, and those have a much more significant mass than the rest of the atom. The next point that we want to make in our notes is one of the most important in this introduction, and that is about what we call the atomic number of an element or of an atom. The atomic number, which is given the symbol Z, is the number of protons in the nucleus. And this is what is going to determine the identity of an element. So, very important to know that, for instance, if the atomic number is 6, then that means we're talking about a carbon atom. If the atomic number is 8, that means we're talking about an oxygen atom. If we are talking about a magnesium atom, then the atomic number is 12, and that means it has 12 protons in its nucleus. So the atomic number is what's going to identify an element. And those are always going to be printed on periodic tables in a really clear place. They're whole numbers, usually printed in the top or bottom of the field on the periodic table. Every periodic table is a little bit different, but you can see the periodic table is going to list the elements as you read left to right in an order of increasing atomic number. While we are considering how many protons an atom has, we're often going to want to think about how many electrons it has. And if the number of protons and electrons is the same, for instance, 3 protons and 3 electrons, that would be a neutral atom. But if it's not the same, then that means the atom has a net charge. The net charge of an atom, we want to include in our notes, is going to be equal to the atomic number minus the number of electrons. So if, for instance, we're talking about an atom which has 3 protons, but only 2 electrons, 3 minus 2 is positive 1. If we're talking about an atom which has 8 protons and 10 electrons, then 8 minus 10 is negative 2. The net charge is negative. We're often going to need to consider what the charge of an atom is. And when we're talking about an atom which has a net charge, then we're talking about an ion. And this is a very important term. An ion is an atom with a net charge. And what I mean by that is a net charge which is not equal to 0, right? If the net charge was 0, well, then we would consider that to not be an ion, but just an atom. And there are 2 types of ion that we're going to consider. Cations, which are positive ions, and anions, which are negative ions. And perhaps this is easy to remember if you notice that the word cation has the letter T in it, and the letter T looks like a plus. Cations are positive ions, anions are negative ions. So let's talk about how you would tell the difference between a neutral atom and an ion if somebody was writing a chemical symbol down. First of all, If we're talking about an ion, then the net charge is written with a superscript. The net charge of an ion is written as a superscript, and I'll show you some examples. For example, if I were talking about an iron ion, which had a charge of +3, then I'd write Fe3+ in superscript. If we're talking about a calcium cation, calcium cations, we'll learn soon, are positive, and the magnitude of that charge is 2. So I'd call that a calcium 2 cation or a calcium 2+ cation. Sulfur typically forms anions, which have a negative charge. Specifically, the charge is 2-. So it's a negative charge with a magnitude of 2. Sodium, on the other hand, forms cations, usually with a charge of +1. And you'll notice I didn't write 1+ or +1, I just wrote plus. And this is often done if the charge is only 1. People will just write a plus instead of a number. As a matter of fact, sometimes if a charge is 2+, they'll write ++, but I prefer not to do that, and it's always okay to add this number. Usually it's written as 1+ and not +1, but it is sometimes dropped when the magnitude of charge is just 1. So for instance, fluorine is usually 1-, and people will usually just write F-. It's also important to note that if no charge is written, we can assume that an atom is neutral. If no charge is written, assume neutral. In other words, if you just see Fe, then we assume that it's a neutral iron atom. And the only way it could be neutral is if there's an equal number of protons and electrons. So iron, if you find it on the periodic table, you'll notice it is element number 26. If it's a neutral iron atom, then there must be 26 electrons to match its 26 protons, otherwise it wouldn't be neutral. So by looking at a chemical symbol, we can figure out how many protons and electrons there are. If you see just a symbol without a superscript, we assume it's neutral. So sodium has 11 protons, and it has, if it's neutral, 11 electrons as well. So what does this mean if it's a sodium cation? Well, it must have 11 protons because it's sodium. And if it didn't, then it wouldn't be sodium. Remember, the number of protons, the atomic number, defines what element it is. So if it is sodium, it has 11 protons. And if it has 11 protons, it is sodium. But whether it's a sodium cation or a neutral sodium anion depends on how many electrons it has. Of course, if it's neutral, it's got just as many electrons as protons. But if it's a cation, that means it has a surplus of positive charge. That means a deficiency of negative charge or a deficiency of electrons. So this sodium cation has 11 protons, but only 10 electrons. And that's going to be something that's important to practice. So here's a few other examples we can look at. For instance, what's the total number of protons and the total number of electrons in these? A bromine anion called bromide, a magnesium cation, or an oxygen anion. How many protons are there and how many electrons are there? Let's see if we can answer those questions before we move on. So there's the answer to those questions, and it is always going to be important to keep track of those charged particles of an atom. How many protons, how many electrons can always be determined when you're given the symbol of an atom or of an ion. So the last concept that I want to include in these notes is one you may have heard before. Opposites attract and like charges repel. So I'm going to write opposite charges attract, and I'll draw just a simple picture here of a positive charge and a negative charge and show that they're attracting each other. There's going to be attractive force between oppositely charged particles. And I'm going to write like charges repel. And I'll draw two examples here. One is, what if I had a positive charge and a positive charge? Well, there's going to be a repulsive force there. And what if I had a negative charge and a negative charge? Also, a repulsive force. In other words, two electrons would repel each other, two protons would repel each other. And this is going to be a guiding principle in a lot of different chemistry concepts. So it's important to understand the basics of what we call electrostatic forces, electrostatic attraction and repulsion.